Good afternoon, everyone, and welcome to this lecture. This is lecture number 3. We are dealing in heat transfer, and in this lecture, we will deal with radiation, which is the major point. But before coming into radiation, we have to deal with one more mode of heat transfer. You may not get any numericals on this, but we'll quickly go through this, and that is known as convection. Heard about the term convection? Convection. Now, in this mode of heat transfer, heat is transferred by the actual movement of the material medium. You have seen water boiling, yes or no? Have you seen water boiling? Have you seen water boiling? Have you seen water boiling? How does water boil? When you are putting water in a beaker, what happens is the first thing that gets heated up is the bottom of the beaker. Yes or no? Once the bottom of the beaker gets heated up, it heats the water which is present at the lowest point, lowest surface. Then this heated water becomes light and it goes up, colder water comes down, and in this way the entire water gets heated up. The entire water gets heated up. The entire water gets heated up by the actual flow of water. Hot water goes up and colder water comes down. So there is an actual transfer of material medium here. Yes or no? This type of mode of heat transfer where heat is transferred by actual movement of material is known as convection. And as you can see, there are two types of convection. One is known as natural convection, which we saw in case of water boiling, or if you have, this is winter time in the north of India and it's getting a lot of chilly waves. If you burn a fire, and even if your hands are far away from the fire, you will feel warm air coming towards you. The air which is near that burning fire will get heated up, heated air will go up, actual flow of material medium. This type of convection is known as natural convection. For convection is for a convection where heated air is thrown inside a room. You have room heaters, that is forced convection. You are forcing the air out, or colder airs with an AC. You are forcing the air out into the room. That is forced convection. Do we understand this? Yes or no? I'll give you 2 minutes to note it down fast. What you can also note here is the formula for this convection. You will never require to use this formula. H into A into T minus T naught. H is the constant of proportionality. Normally they will give you the value. A is the area of the body which is getting heated up. T is the temperature of the body. And T naught is the temperature of surrounding. So this is the vague formula for heat loss due to convection. Then we come to the next heading, radiation or thermal radiation or simply radiation. We might have heard this term, thermal radiation.
Yes, sir.
What is this? Thermal radiation. Now, is the process of transfer of heat. Is transferred from one place to another place without heating the medium in between. So when it is traveling from one place to another place, it is not heating the intervening medium. This process of heat transfer is known as radiation. This process of heat transfer is known as radiation. So what is radiation? Now when we use the term radiation, radiance means the process by which this energy is produced, this thermal energy is produced. Radiation is a very, very broad term. Radiation also refers to the process by which this energy is transmitted and radiation also refers to the energy itself. So, when I say a body is emitting thermal radiation, it means the energy that it is emitting is thermal radiation. The process by which it is emitting that energy is also radiation. The process by which that energy is transmitted is also radiation. So radiation means everything about thermal energy. Do we understand what I have said?
Yes.
The energy is transferred from one place to another without heating the intervening medium. This does not require the presence of any material medium. It will not heat any material medium. It does not require any material medium. It can travel in vacuum. This is the process by which energy emitted by the sun reaches Earth, is by the process of radiation. Do we understand this?
Yes.
Everything is radiation. As I told you, the term radiation is also another term for electromagnetic waves. That means the energy which is emitted is also known as radiation. I've already told you that. Yes or no? Yes or no?
Yes, sir.
So this is radiation. All bodies will emit energy by this process, whether they are solid bodies, whether they are liquid, or whether they are gases. The energy emitted is known as radiation. The process by which energy is emitted is known as radiation. The process by which it is transmitted is also known as radiation. Everything is radiation. I'll give you 2 minutes to note this down. Then we move ahead and see the various properties of radiations. First, let me explain them and then I'll give you time to write them. All these properties may come as questions in your exam. All bodies will emit radiation simply because their temperature is above zero. So any body which is above zero is going to emit radiations. The energy it emits is known as radiation. The process by which energy is emitted is also radiation. The process by which is transmitted is also radiation. We understand this. And the energy is also radiation. Do you understand this?
Yes, sir.
Now, all these radiations are electromagnetic waves and they consist of electric and magnetic field which are perpendicular to each other. Okay. A body which is at a lower temperature will emit less radiation. A body at a higher temperature will emit more radiation. Okay. We'll see all these things at different points as well. When a body is emitting radiations, it emits radiations of all wavelengths. But you increase the temperature, and we will see this law is known as Wien's displacement law. We will see this in great detail. Right now, you can just write here in bracket Wien's law. Wien's law. And we will study this under the heading of Wien's law. All these thermal radiations, they are electromagnetic waves, so they can travel in vacuum and they travel with the speed of light. Do we understand this? Yes or no? No or yes?
Yes, sir.
Just like light, they can be reflected or they can be refracted, diffracted, and polarized. So these are some of the properties of radiations. One more property is left. One more property is left, and I'll try to put that property also, so that all the properties are there in one sheet. So I'm trying to make space for that property. Okay, so this is the last property. Radiations which are emitted by a point source is inversely proportional to R square. I told you that, yes or no? Intensity is
Yes.
proportional to 1 by R square. Yes or no? In waves.
Yes, sir.
Now you note this down. I'll give you 2 minutes. So take these 2 points as well. These thermal radiations are always in the infrared region. Their wavelength is more than red. Therefore, they are also known as infrared rays. When they fall on a body, incident on a surface, they will exert force. Because of that force, they will exert pressure. That pressure is known as radiation pressure. Well, let us now move on to certain definition. Before moving on to let us first do this, and we write the heading Prevost theory of exchange. This is a very elegant theory that explains what happens. Now, in short, if I say, we have already seen it in the properties of thermal radiations that all bodies, no matter what their temperature is, because absolute zero temperature is not possible, so temperature of any body is obviously more than 0 Kelvin. So all bodies are going to radiate or emit thermal radiations at all temperatures. Do we understand this?
Yes, sir.
All bodies, sorry, got a phone. Let me just silent it. All bodies are going to emit thermal radiations at all temperatures. We understand this point number one.
Yes, sir.
Point number two, the amount of thermal radiation radiated per unit time, and we will see this formula. It will depend on the nature of the surface, its area, and its temperature. Yes or no?
Yes, sir.
If the body is at a higher temperature, it will radiate more. If the body is at lower temperature, it will radiate less. Yes or no?
Yes, sir.
Also, a body will absorb part of the thermal radiation emitted by the surrounding bodies. Yes or no?
Yes, sir.
If a body radiates more than it absorbs, its temperature falls. If a body radiates less than what is absorbed, its temperature rises. And if the temperature of body is equal to the surroundings, that means it is absorbing and radiating at the same rate. This is known as the Prevost theory of exchange. It, in very simple terms, it tries to make you understand what is thermal radiation, why is the temperature of a body rising, and why is the temperature of a body falling. If there is hot tea which is going to come and I keep that hot tea on this table, after some time it will come to room temperature. If I bring a chilled bottle of cold drink and I put it here, that chilled bottle of cold drink is going to get warmer. Now do you understand the reason why a hot tea becomes colder and a chilled cold drink gets warmer? A hot tea is emitting more radiations and absorbing less radiations, whereas a chilled cold drink bottle is emitting less radiations and absorbing more radiations. Do we understand this?
Yes, sir.
This, my dear friend, is known as Prevost theory of exchange. Do we understand this?
Yes, sir.
Then there is something known as the Prevost. Okay, first write this, then we will go ahead. The next thing that we are going to write is black body, Kali body. Black body or a perfectly black body. What would be a perfectly black body? Now, as we have seen by Prevost's theory of exchange, a body emits thermal radiation, at the same time it absorbs the thermal radiations which are emitted by nearby bodies. What is a black body? What do you understand by a black body? A body which absorbs a body which absorbs all the heat radiations or whatever wavelength which is falling on it is known as a perfectly black body, or sometimes it is also known as Ferri's black body. This is a simple example of a black body. Spherical body, very small hole, whatever radiation or light is entering into it, there is a bulge P, and this light will get absorbed and this radiation will get absorbed and it will never be able to come out. This becomes an example of almost a perfectly black body which absorbs 99% of the radiation. Do we understand what is a black body? Yes or no? No, yes.
Yes, sir.
I'll give you 2 minutes to note it down. Let's now move ahead and see some terms and try to understand their meaning. Remember, this entire chapter is about understanding the various terms that are going to come. If we understand those terms and understand them nicely, this chapter is done. So let us try to understand those terms. Once we understand those terms, this chapter should be a cakewalk. So terms used in radiation, and I'll try to put them systematically. Terms used in radiations. Terms, meaning of terms. The first term that we are going to see here is known as absorptive power. Absorptive power, or some people may call it absorptance. Absorptive power or absorptance. What do you mean by this absorptive power or absorptance? It is written by the small letter a. It is QA divided by Q. Now, what is QA and what is Q? Q Q is the total radiation that is falling on the body. It's the ratio. Absorptance or absorptive power is a ratio. It is the ratio of the total radiation which is falling on the body to the radiation which is absorbed. Radiation which is absorbed. That is known as absorptive power. Then what is the next thing? Reflecting power or reflectance. Reflective power or reflectance. This is normally denoted by R, that will be equal to QR divided by Q. Do you understand the meaning of the terms? Yes or no? What is QR and what is Q? First listen to me, then I'll give you time to write. Transmitting power or transmittance. Denoted by the letter small on color. Denoted by the letter small. Denoted by the letter small t. Q transmitted divided by total Q falling. Do we understand this?
Yes, sir.
If I write this together, which I'm going to do on the right hand side, please give me time to explain, then you can write it. Total amount of heat which is falling on a body will be the sum of QR, QT and QA. Yes or no?
Yes, sir.
So R plus T plus A would be known as, or R plus T plus A would be equal to 1. Yes or no?
Yes, sir.
Then it is easy to understand. If A is 1, other things are 0, it will be a perfect black body. If R is 1 and other things are 0, it is a perfect reflector. If T is 1 and the other things are 0, it is perfect transmitter. Do we understand this? Yes or no? No or yes?
Yes, sir.
And this one more diagram I can write here or draw here. This is the diagram of the total energy which is falling. Do we understand this?
Yes, sir.
Energy is falling, incident, some part of it reflected, some part of it transmitted, the rest of it is absorbed. Yes or no? No or yes?
Yes, sir.
I'll give you now 2 minutes to note it down. Let us now move ahead. We have already seen this term, absorptive power. Yes or no? Absorptive power or absorptance is the total energy absorbed divided by total energy which is incident. Yes or no? No or yes?
Yes,
Total
sir.
energy absorbed divided by total energy which is incident. Now, this is written by the letter A, small letter A. Now, there is one more term that is defined here, and that is known as spectral absorptive power. Spectral absorptive power A lambda. Now, what is this spectral absorptive power? Any idea?
No, sir.
Now, when energy is falling on a body, it is definitely not of a single wavelength. The energy which falls on a body can be of a combination of any wavelength. It could be a single wavelength. When thermal energy is falling on a body, it is not of a single wavelength. The wavelength of that radiation can vary from 0 to infinity. Yes or no?
Yes, sir.
If you take a unit wavelength, how much energy of a unit wavelength is falling on the body, and how much energy of that unit wavelength is absorbed, that is known as the spectral absorptive power. Do we understand this? For example, 1450 to 1550, one unit wavelength, or 1450 to 1451, I have taken one wavelength. How much energy in this wavelength is falling off the body, and you find out how much energy of this wavelength is absorbed by the body. How much energy is absorbed divided by how much energy is falling is known as the spectral absorptive power. Do we understand this?
Yes, sir.
There is a relation between spectral absorptive power and spectral emissive power. Spectral absorptive power and total absorptive power A will be equal to 0 to infinity A lambda D lambda. What does that mean? If I draw a graph, between A lambda and lambda, the graph may be something like this. The area under, so basically it is what it is telling, what for different wavelengths how much is the absorptive power. The area under this graph will give me the total absorptive power. Do we understand this?
Yes, sir.
Because the energy which is falling on a body is not of a single wavelength. It can be of wavelength starting from 0 to infinity. The area under this graph gives you the total absorptive power. Spectral absorptive power is the absorptive power for one unit wavelength. We understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Let us now move ahead and write the next heading. And the next heading is emissive power, or you may call it total emissive power. Emissive power. Written by the letter capital E. Emissive power or total emissive power. What is this total emissive power or emissive power? It is the energy emitted per unit area per unit time by the body. Remember, absorptive power is a dimensionless quantity, but emissive power is not a dimensionless quantity. In fact, it has a dimension. What? Oops, what is happening? It has a dimension. Energy is Joule per unit time is power. Power per unit area, watt per meter square. Energy radiated per unit time, per unit area by a body is known as its emissive power. How much energy it is emitting per unit area per unit time. Do we understand this? Now this emissive power is for all wavelengths, because when it is emitting power, when it is emitting radiations, when it is emitting energy, I am at some temperature, I am emitting energy, I am emitting energy of all the possible wavelengths. Do we understand this? That is known
Yes, sir.
as the total emissive power or the emissive power of the body. Why we are so selective? Because there is one more term that we have to understand here. And please understand this term, then I will give you time to write. That term is spectral emissive power. Spectral emissive power. It is denoted by E lambda. Now you would be able to tell me what would be spectral emissive power. It is the emissive power for a given wavelength. How much energy per unit area per unit time for a given wavelength is emitted, that will be known as spectral emissive power. E will be equal to integral from 0 to infinity E lambda d lambda. Why I'm writing dy? E lambda d lambda, or you can write E lambda is dE by d lambda. Are you understanding what I'm doing here? If I draw a graph between lambda and E lambda, the area under this graph will be equal to the total emissive power. Do we understand this? Or this is going above our head saying bye-bye? Do we understand this? Do we understand this?
Understood, sir.
You have 2 minutes to give to note this down. Then we move on to one more term, and that term is known as emissivity. Don't get confused between these three terms. There is a lot of confusion between these three terms: emissive power, spectral emissive power, absorptive power, spectral absorptive power, and emissivity. Emissivity, this gentleman is denoted by small e, remember that. Emissive power is denoted by capital E. And what is emissivity? It's the ratio. Emissivity of a body is a ratio. Ratio between what? Ratio between emissive power of a given body at a given temperature divided by the emissive power of a black body at the same temperature. I hope you understand this. Yes or no? No or yes?
Yes, sir.
It is the ratio of emissive power of a given body to emissive power of a black body of the same size, same shape, and same dimension. Do we understand this? Sometimes I have also seen a term called spectral emissivity, E lambda. If you have to find out E lambda, then what do? You divide E, capital E lambda by E naught lambda. You find the ratio of spectral emissive power of a body divided by the spectral emissive power of a black body at the same temperature with the same dimension, you get E lambda. Do we understand this? So sometimes you might encounter this spectral emissivity. This is nothing but this. Do we understand this? I'll give you 2 minutes to note this down. The next heading that we are going to write is Kirchhoff's law. And what is this Kirchhoff's law? It simply says that if you find out the ratio is not a ratio, if you divide the emissive power to absorptive power of any body, let me not write this definition, may not give you directly because not the ratio. You can write it like this. You can write this one. You find out the ratio of emissive power to absorptive power. Is not a ratio because they are not same, but it's easier to say it in this way. If I find the ratio of emissive power to absorptive power for any body at a given temperature, that ratio is going to come same as the ratio of emissive power to absorptive power of a black body of the same dimension at the same temperature. So this is what this Kirchhoff law say. E by A, the ratio is constant, and E by A is always equal to E by A for a black body. But you understand that we understand that the absorptive power for a black body is always equal to 1. Yes or no?
Yes, sir.
Therefore, E of any body divided by A of that body will be equal to the E of black body. Or I can write it as like this: E of body divided by E of black body would be equal to A of the body, absorptive power of the body. Do we understand this? Yes or no? No or yes?
Understood, sir.
Now, E of the body divided by E of the black body is equal to the emissivity of the body. Yes or no?
Yes, sir.
That means the absorptive power of the body. Basically, what Kirchhoff's law is saying is absorptive power of the body is actually equal to its emissive power or emissivity. Yes or no?
Yes, sir.
That means Kirchhoff law is saying if you have higher emissive power, you will have higher absorptive power. Or Kirchhoff law is simply saying that good absorbers are bad reflectors, are bad transmitters, but good absorbers are good emitters. Do we understand what I'm saying?
Yes, sir.
Good absorbers are good emitters. Black body is a perfect absorber. Black body is a perfect absorber and a perfect emitter. Do you understand what I mean by this?
Yes, sir.
Absorptive power of a body is equal to its emissivity. That is what Kirchhoff's law mean in a simple way. Now, if you want to calculate this for any particular wavelength, you can also write this Kirchhoff law for that given wavelength. For that given wavelength, the ratio of emissive power of the body to the absorptive power of the body for that particular wavelength will be equal to the emissive power of the black body for that particular wavelength. I hope you have understood this. Whatever we are saying for total emissive power, the same thing we are saying for spectral emissive power. Do we understand this?
Yes.
So here we go. So basically, what we can say from this Kirchhoff's law, the first point that we can say from a Kirchhoff's law, if the temperature is constant, the spectral or the emissive power of a black body is constant because the ratio is constant. Do we understand this?
Yes, sir.
Then again, we can say a good absorber will be a good emitter, a bad absorber will be a bad emitter. Yes or no? No or yes?
Yes, sir.
Note this down, please. This is the first question. This has been taken from one of your previous papers. Let us get the answer for this one. An ideal body at room temperature is thrown into a furnace. After what will be observed? So, what is the What is the answer for this one? Can I have an answer for this one?
The option B.
Option?
B, sir.
It is the darkest body at all times. No, that is not the correct answer. Think again. That is not the correct answer. Think again. I'm giving you time. Yes.
Option D, sir.
Option D. It is brightest to begin. It is darkest to begin with. And after some time, it will not be able to recognize because it will absorb and it will emit at the same rate. So it will get to the temperature of the furnace and you will not be able to distinguish it. Do we understand this?
Yes, sir.
Great. Let us move ahead to this question. A body is in thermal equilibrium with the surroundings. Which option is correct? A body is in thermal equilibrium with its surroundings.
Option B, sir.
Option B, amount of radiations emitted and the amount of radiations which are absorbed. It will absorb and emit at the same rate. We have already seen that. Well done. Next one. If the transmission power of a surface is 1 by 6, the reflective power is 1 by 3. What will be the absorptive power? I'll give you a minute to do this. Option B is correct. Remember, transmittive power T plus reflective power R plus absorptive power A must be equal to 1. Transmittive power is given as 1 by 6, reflective power is given as 1 by 3, so if absorptive power is 1 minus 1 by 3 plus 1 by 6, it will be 1 by 2. The answer A is also 1 by 2. Do we understand this?
Yes, sir.
This is the next question. In the graph shown in the diagram represents the variation of temperature T of two bodies X and Y having same surface area with time T due to emission of radiation. Find the correct relation between the emissivity E and absorptive power A of the two bodies. I'll give you 2 minutes to give me the answer. So what you can see here, beta, is initially both the bodies were at the same temperature. But after that, if you find at any time t, this body, X body, the temperature of the X body is less than the temperature of the Y body. Yes or no?
Yes.
Yes or no? Yes or no?
Yes, sir.
That means X body has radiated more heat compared to Y body. Yes or no?
Yes.
That means this option and this option has to be wrong. The emissive power of the X body must be more than the emissive power of the Y body. Yes or no?
Yes, sir.
Now I have already told you that emissive power E is equal to the absorptive power A. Yes or no?
Yes, sir.
If emissive power is more, then the absorptive power is also more, and the correct answer is option C. Option C is the answer, my dear friend. Option C. Have you noted it down?
Yes, sir.
Then there is one more question coming for you. Certain substance emits only wavelengths lambda 1, lambda 2, lambda 3 and lambda 4 when it is at a high temperature. When it is at a colder temperature, it will absorb which of the wavelengths? I'll give you 2 minutes to think on this. It is definitely option D. Whatever it emits, it must absorb the same thing. That is what Kirchhoff's law says. So the correct option has to be option D. Do we understand this? Yes or no? No or yes?
Yes.
Then comes this question. The next one. And I hope you can give me the answer for this one. The following figure shows two air-filled bulbs connected by a U-tube filled with alcohol. What happens if the level of alcohol, if an electric bulb is lighted between the two? One side is a black air-filled bulb. The other side, it will be a light colored bulb. The answer is option A. The black bulb will absorb more, so it will expand more. If it expands more, the level of liquid will fall, and the white painted bulb will be expanding less. So option is A. Do we understand this? We get this, bacha? Okay. Let us move ahead. The next heading that we are going to write is the energy spectrum. What is this energy spectrum? So basically, scientists have studied the spectrum of radiations emitted by black bodies at different temperatures, and they have seen what is the graph that you get. So basically what they have studied, name of the scientist is Langley and Lummer. So if you have a black body, and if you heat up this black body at different temperatures, they have plotted how much energy of which radiation is emitted by that body. You can see on the y-axis we have E lambda, and on the x-axis we have lambda. So I have plotted a graph between E lambda and lambda at different temperatures. Do we see this graph? First, let me explain, and then I will give you time to note this. What are the things that we see from this graph? Very important points here. Very important points here. The first point that we see here, that energy is not equally distributed among the different wavelengths. You can see of one particular wavelength, energy is maximum, but if you go on the left of that or on the right of that, the energy is not equally distributed. That means any body which is emitting radiations, it does not emit equal energy radiations for all wavelengths. For some wavelengths, it will emit maximum energy, and for the other wavelength, it will emit very less energies. Do we see this? Yes or no? Now, if you see at a given temperature, we have plotted the graph at 3 temperatures. At a given temperature, the energy first increases with wavelength, it reaches a maximum, and then it decreases. Do we see this? For a given wavelength, you can see this yellow graph. For a given wavelength, the energy first increases, then the energy decreases. Do you see this? Yes or no? No, yes.
Yes, sir.
With increase in the temperature, and that is the most important fact, which is known as your Wien's law. With increase in temperature, you can see the wavelength with the maximum energy decreases. You can see temperature T3, this is the graph. Temperature T2, this is the graph. And temperature T1, this is the graph. You can see lambda 1, which is the energy, which is the wavelength with the maximum energy, is more than lambda 2 and more than lambda 3. That means higher the temperature, the wavelength with maximum energy decreases. Do we understand this?
Yes, sir.
That means lambda into T is a constant, that is known as Wien's displacement law. This is point number 1, this is point number 2, and this is point number 3. Now, just remember, Vibgyor. Do you remember this Vibgyor?
Yes, sir.
Lambda of red and lambda of violet. This is how it goes. Lambda of red is more than all these lambdas. Yes or no?
Yes, sir.
When you start heating up a body, let us say you have a metal body, iron body, you start heating up that body. First of all, the body just remains its original color. But when the temperature rises further, you will see this iron
Red
or
color.
metal body becomes red hot. We call it red hot.
Yes,
Why
sir.
it becomes red hot? Why it becomes red hot?
Sir, as we are giving energy, it absorbs some and emits some.
It is when you increase the temperature, it is emitting radiations. It is emitting radiations of all possible wavelengths. For one wavelength, it is emitting maximum energy. When you keep on increasing that temperature, that wavelength becomes less and less. So when that wavelength comes in the red zone, the body looks red hot. If you heat it further, the temperature will change from red to orange because now it will start to emit orange radiations more because the temperature is falling, temperature is rising and wavelength is falling, wavelength with the maximum energy. Then it will turn yellow, then green, then blue. Your flame of your gas stove is blue. You put water onto it, it becomes red, which is at a higher temperature, the blue flame or the red flame? The blue flame is at a higher temperature. Looking at the color of the flame, you can tell which is the hotter one. Blue one is hotter. Then it will turn indigo. Peak summer. How does the sun look like? Indigo. Red hot. When the sun is setting, red hot. It looks calmer. When it comes off, violet. Higher temperature. Do we understand this or this is gone? Above or at saying bye bye?
Understood, sir.
Wait, as soon as the temperature increases, the wavelength with the maximum energy decreases. The iron block will first become red, then orange, then yellow, then green, then blue, then violet, then indigo, then violet, and after violet, we will stop seeing the color. Do we understand this or this has gone above our head saying bye bye, bye bye, bye bye?
Understood, sir.
When you increase the temperature, the energy of all wavelengths increase. You can see this. Temperature T1, the graph is very small. Then temperature T2, the graph becomes more. At temperature T3, the graph becomes more high. It's happening because the energy is increasing. As the temperature is increased, the energy increases. Do we understand this or this is gone above our head saying bye bye, bye bye,
Understood, sir.
bye bye, bye bye? Okay, I can only put these many things right now. So I will now request you to note these 4 points down and then I'll give you the other 2 points. You noted it down? Yes or no?
Yes, sir.
We have seen the area under E lambda graph will give us the total emissive power. Yes or no?
Yes, sir.
And we will find, not in today's class, but in tomorrow's class, that this E lambda, D lambda ka integral, which is the total emissive power, it will be coming proportional to T raised to the power 4, which is the Stevens law. Basically, the fifth point is telling us if you find out the area under this graph from 0 to infinity, that will give you the total emissive power E. Yes or no? No or yes? Do we understand this?
Yes, sir.
Very important point which we missed. The energy maximum corresponding to the wavelength of maximum emission. Total energy is proportional to T raised to the power 4, but energy corresponding to the maximum emission is proportional to T raised to the power 5 because it is E lambda divided E lambda divided by D lambda. For what I'm saying, dE by D lambda, and it will come proportional to T raised to the power of 5. Do we understand this? Note
Yes, sir.
this down. I'll give you 2 minutes. Okay, so we have noted this down, yes or no?
Yes, sir.
Okay, I'll just give you these 2 graphs so that you don't get confused between, sometimes the graph is between E lambda and lambda, and sometimes just to confuse you they might give you the graph between E lambda and frequency. What happens when the temperature is increased? What happens with the frequency of radiation which has got maximum energy? Remember, the frequency increases because frequency is inversely proportional to lambda. Do we understand this? Yes or no? No, yes.
Yes, sir.
So these are the graphs for frequency. So you can draw these graphs as well. I'll give you 2 minutes. Same thing, just explain in terms of this graph. This peak, height of the peak, energy for maximum lambda is proportional to T raised to the power 5, but the total energy is proportional to T raised to the power 4. This is Stevens' law. So this is just shown in terms of a diagram. Do we understand this?
Yes, sir.
Okay. Do you want to note this down or you have already noted this down?
1 minute, sir.
Okay. Then I'll give you time to note it down. Then comes this question. This is a question taken from previous year JEE. And the question is pretty simple, straightforward. Remember, three different black bodies are there, not a single black body. The plots of intensity versus wavelength for three different black bodies at three different temperatures, T1, T2, and T3 are shown. Their temperatures are such that which is more, which is less.
Sir, option B, sir. T1 is greater than T3 is greater than T2.
That is correct. You must remember when temperature increases, the curve will shift towards the left. Do we understand this? The area
Yes,
under the
sir.
curves are different because it's for three different bodies and therefore they have three different graphs. But Wien's displacement law have to be followed. Do we understand this or this is going above our heads? Saying bye bye.
Understood, sir.
Then this is the next question. The adjoining diagram shows the spectral energy distribution E lambda of one black body, same black body, at two different temperatures. If the area under the curves are in the ratio 16 is to 1, what is the value of the temperature capital T? You have 2 minutes to give me the answer. And the answer is definitely 4000. How did we get this? You must remember that the total energy is directly proportional to T raised to the power 4. Yes or no?
Yes, sir.
And this is nothing but the area of this graph. So A1 by A2 will be equal to T1 by T2 raised to the power of 4. Yes
Yes,
or
sir.
no? Energy has become 16 times and energy is proportional to T raised to the power 4. So temperature has to become 2 times. Temperature becoming 2 times, therefore the answer has to be 14,000 4,000 kelvins. Do we understand this? Remember, this
Yes, sir.
answer is always in kelvins. It is never in degrees Celsius. Physics is never about degrees Celsius. The answer will always be in Kelvin. Do we understand this?
Yes, sir.
Comes the next question. Following graph shows the correct variation in intensity of heat radiation by a black body and the frequency at a fixed temperature. Which is the correct? I'll give you 2 minutes to think about it. Well, as I have already given you the diagram, this is the graph between, if this would have been lambda, this would have been the correct graph. Yes or no?
Yes, sir.
If this was lambda, then this was probably the correct graph. Yes or no? But this is F, so this graph is wrong. This graph is wrong. Only the correct options can be this one or this one.
Yes, sir.
Then you have to see infrared red wavelength is more, so frequency has to be less. So the first one would be infrared, then visible, then ultraviolet. These things are same here. You just have to look at the temperature. More temperature means more area. More area means more energy. The only thing that satisfies this is option C. And option C happens to be the right answer. Do we understand this? So this has gone above our head. Saying bye bye. Bye bye.
Understood, sir.
Okay then. We will move ahead and officially write Wien's displacement law. Wien's displacement law. Now, we must understand that whenever a body is heated, it will emit radiations of all possible wavelengths. Yes or no?
Yes, sir.
But for one particular wavelength, the energy emitted is maximum. Yes or no? No or yes?
Yes, sir.
We have already seen that. Yes or no?
Yes, sir.
Wien's law says that as the temperature is increased, this maximum energy wavelength is decreased, or lambda m is inversely proportional to T, or lambda m into T is a constant. This statement is known as Wien's displacement law. This statement is known as Wien's displacement law. So Wien's displacement law is just saying that this graph, which we have already seen, holds true. We have already seen this graph. Yes or no? No or yes? If you
Yes,
increase
sir.
the temperature, the maximum wavelength, the radiation with maximum, the radiation which has maximum energy, the wavelength decreases. Yes or no? No or yes?
Yes, sir.
If we draw the graph between lambda m and t, lambda m into t is a constant, remember my dear friends. So graph between lambda m and t would be a rectangular hyperbola. Do we understand this? Yes or no? No, yes.
Yes, sir.
The value of this b you may not know, but for a black body, this b is 2.89 into 10 raised to the power minus 3. So I'll just give you that value and then you can note down this one where it is. This, my dear friends, is known as the Wien's displacement law. Everyone understands this Wien's displacement law?
Yes, sir.
I'll give you 2 minutes to note it down. Then I'll give you one problem so that you can do this and then we can wind off today's class. This one, a black body at temperature 200 Kelvin is found to emit maximum energy at the wavelength of 14 micrometer. When its temperature is raised to 1000 Kelvin, what is the wavelength at which it will emit maximum energy? I'll give you 1 minute to solve it. Answer is option C. We all know lambda m into T is a constant. So lambda 2 by lambda 1 will be T1 by T2. Temperature has become 5 times, so lambda will be divided by 5. The only option which matches here is 2.8 micrometers. Do we understand this, or this has gone above our head saying bye bye? Bye bye, bye
Understood, sir.
bye, bye bye. Well then, Congratulations. We have come to the end of this particular topic. Tomorrow, that is Saturday, by all means, we will be ending up with thermodynamics. And on Sunday, we will start with electrostatics, your favorite topic. So, on that note, I will end today's class. I hope you have understood what we have done. I've already sent you the sheet. Did you solve that sheet? Yes or no? Huh?
Solving, sir.
Solving, sir. When will you solve, sir? Saturday, tomorrow, sir. Tomorrow you must finish because from Sunday you will have to move on to electrostatics. On that note, I'll end the class. Take care. God bless you all.